So in homework 5, you basically you have to do this matrix product with this so-called DNS scheme, and so there are essentially two main parts. One is or three main parts. One is writing the program. So we'll go over that during these lectures. Second part is sort of running some benchmarks and so on. Okay, pretty straightforward. Then the last bit has to do with a more theoretical kind of analysis of the running time. And so today I'm going to focus a little bit on that. And so hopefully all the concepts that, so all the theory stuff that you do for homework 5 will be covered in today's lecture. So I'm going to start with a simple example and just matrix vector product. So a simple example to kind of illustrate, and then again on Friday we'll focus more on specifically the matrix product and so on. So here I just want to do x equal a times b. So we're going to go over the algorithm, how to do that. But then I really want to focus on this sort of theoretical analysis that you need to do at the end of homework 5. Okay, so you have to do this matrix vector product, okay? X equal a times b. And matrix A, so you want to do this distributed memory with MPI. So these are the input, and this is the output of your algorithm. Okay, and essentially the question is, so you have to perform all these multiplications and additions, and the question is, how are you going to distribute the data? Okay, so essentially, where is the data located? On which process and so on. And this determines, how the MPI implementation goes. So we're going to go over three schemes. First one is to partition the matrix sort of across columns. So you take one row or a group of rows goes to one process. Okay, and so you partition across the rows. Then there's a similar scheme where you partition across columns, but it's very, very similar. And then there's another scheme where you partition the matrix in 2D. Okay, so you get a series of blocks, and each block is then associated with a process. So we're going to see what sort of communication patterns are associated with each decomposition. But then more importantly, we're going to do analysis of the running time of each algorithm to kind of figure out, sort of theoretically, whether one algorithm is superior to the other or not. So let's look at row partitioning. So row partitioning is basically, the idea is you're going to take your matrix, decompose it across the rows like this, and then each column block is stored on a given process. Okay? And so the question is, so you start like this, so the matrix is decomposed like this. You assume that your vector is also distributed in a sort of similar manner. Okay? Well, so for the vector, there's sort of only one way to really distribute it, so this is sort of natural. Now the question is, okay, you want to do A times B. So here, for example, let's take the blue process. Okay, the blue process actually cannot do the multiplication because it has a little bit of the blue here, but it needs the other entries in X, so it can do the multiplication. Okay, so the first step is actually to give to all processes the entire vector B. Okay, and so each process is going to start with just a piece of B. Okay, and then you're going to apply an MPI function so that each process has the entire vector B. Okay, so this is an example of a collective communication that we covered last week. And if you go over different options you have, you'll see that this is an MPI all gather operation. So you're going to call MPI all gather with this input, and then after the function completes, each process has the entire vector, and now you can just do the multiplication. Okay, so you call MPI all gather to do that. Okay, once so just going back one slide, once each process has an entire vector. Okay, and then it has this block, this row of A, then each process can just do the product. There's no further communication, data exchange, you can just do the math, and you have the results. Okay, so step number 2 is just a local product, no communication required. So you can follow this link to get the entire code on GitHub. I'm just going to show you essentially just the core of the code, the part that with MPI and so on. So you call MPI onGather, okay? And the way you do this is you give the address of where your local copy of B is located, okay? And you want to finish with a copy of the full B vector, okay? So here you give, what's the address of my own local copy. Each process has a different copy, different block of B. That's the size of each block, okay, the type, okay? And each process is going to send data of size and local. Okay, and the result is stored then inside of the B vector. Okay, now you have a few rows. You have the entire B, so you can do this multiplication. Now you can see how this looks like. Here, row, so it says from 0 to n local, and this is very common in MPI that there's sort of a global numbering, which is the real row number if you want, and then there's a local numbering for just the rows that you have. Okay, so in the local numbering, I starts at 0, but in reality, this is a specific set of rows in matrix A. Okay, and then you get the subset of the X entries. And so you see that, for example, the matrix may be very large, but you're only processing n local entries in this calculation. Okay, and no further calculation communication is required. Once you have X, you're done with that. Okay. So any question about this implementation? All gather. Okay. So this is a blocking communication. Okay. So the code stops there until communication is complete, and so everybody needs to give address of its own data and where to store the entire B data. And local is the amount of data to send essentially. The amount of data you have, and essentially the amount of data other processes are going to send. Okay. So the second scheme is the column partitioning. So this one, I'm going to go a little bit more briefly over that. It's very, very similar. So we are going to do a partitioning across the columns, but you'll see that actually the steps are sort of closely related to the column partitioning, and in terms of performance and so on, it's almost identical. So these two schemes are sort of sometimes called dual of each other, or they're very closely related. So in the column partitioning, the idea is now each process stores a subset of the columns. So you have all the rows, but just a few of the columns. Okay, again, you multiply by this vector, but every process has a local copy of the vector. So, what's the main difference here is that when you start, each process actually has all the data it needs. Okay, you have a bunch of columns. You have some entries in B, so actually the entries you have exactly correspond to the columns you have. So you can actually fully do the product. Okay, although what you get as a result is just the product for these columns. So it's a partial product. Okay, and so there is another addition here, which is going to be a plus, a reduction. Okay, so now it's more like let's do the calculation with these blocks, we get partial results, then the communication. Whereas in the previous scheme, it was communication, then do the multiplication with no more data exchange. So here, step one is to you do the partial product, each process. So actually, no data exchange is required. Okay, you get partial results for X. Okay, now you need to do an addition. Okay, a reduction across all processes. So we're going to call an MPI reduce. Okay, and so the result may be stored on one process, but then if you maybe want to distribute the result as well, then you're going to take this result here and then scatter it across all processes. Okay, so this is an extra step just so that each process has a little chunk in the output for the output vector x. Okay, so again, reduction here with collective communication, reduction across all processes, get the final result, and then scatter so that everybody has just one piece of the data. Okay, so here I'm going to skip the details of the code, but it's an NPI reduce followed by an NPI scatter. Okay, again, this is doing the addition to finish off the matrix vector multiplication, and then this is just to sort of change the data layout. So in principle, you end up with one process having the result. So you can scatter it, so every process has a little chunk of the result vector x. Okay, so the performance is very similar to row partitioning. So it's a little bit like, first one is doing communication and then the multiplication. The other one is let's do the multiplication and then the communication. But at the end of the day, it's kind of very similar. Okay. All right, so you have this. Okay, and so now I want to contrast this against the last approach, which is this 2D partitioning. Okay, and so I'm not going to show you benchmarks, but if you look at this row partitioning, or column partitioning, the equivalent, as you keep increasing the number of processors assigned to this task, or the number of ranks in MPI that are doing this matrix vector multiplication, then you will see that the efficiency goes down, in the sense that the runtime initially goes down very rapidly, but at some point, as you keep increasing processes, the runtime decreases more slowly. In fact, at some point, it may stop going down altogether. In fact, if you keep going, it may even go up. Okay, so that's definitely very bad. So there is a better approach, which is this 2D block partitioning. So I'm going to explain again the algorithm, but then I want to focus on how do we model the running time of these different algorithms, and how do we compare these running times. So it's a theoretical exercise just based on the model of the running time. Okay, but it's something very important to understand how efficient parallel algorithms are, and something you have to do in homework 5. So let's look at this 2D block partitioning. So generally speaking, here, at the very high level, we had a matrix. So we decided to do either this row partitioning, this column partitioning, but it seems more natural that we should subdivide the matrix into blocks and assign a given block to a given process. Okay, so a process is now responsible just for taking this block, multiplying by the corresponding entries in B, okay, and then you get a partial result for X. There's going to be a reduction to get the full result, okay? And so it definitely looks more complicated. In fact, if you think about it, it kind of feels that there should be more communication, because you have all this partitioning and so on. There's going to be more movement of data, but actually you'll see in the analysis that it turns out that this is the more efficient method. So let's look at the different steps, and yeah, I guess I'm changing. I just changed all those lectures, so there was sort of a follow-up on Friday, which I guess will be canceled. So probably will not show you how this is implemented. I will just jump in, what needs to be done in homework 5. And homework 5 is sort of a variant on this, so it's all kind of related. But here I'll just show you the sort of high-level picture, and I guess we'll just skip the implementation, and then on Friday I'll just focus specifically on the matrix product you have to do for the homework. Okay, we'll kind of skip the code for that. But okay, so essentially the steps are as follows. So first, when you do this blocking, things become a little bit more complicated when you start, and you'll see that in homework 5 you have a similar situation. That the vector B is sort of one-dimensional; it's just a vector, whereas you have this 2D partitioning. So in principle, it's not reasonable to assume that B is stored in every process, instead we're going to assume that, for example, B is only stored in this, the processes with, say, j equals 0, okay? Right? So we're going to assume that you start with all processes having B in this column. In homework 5, well, you know, you always have to make these decisions about where the data is. In homework 5, it's even more dramatic. We're going to start assuming that the matrix is actually stored on node 0. So node 0 actually has the entire matrix. And so the first step will be sending blocks from node 0 to some of the other processes. So we'll look at that. So here we're going to assume that, you know, this column j equals 0 actually has B. And so for example, the first block B here corresponds to this column. So this is sort of fine, it's in the right column. But this guy needs to move to the second column, corresponds to the second column in the product. This guy, third column, and this guy, the last column. So the way to do this, and there's going to be a very similar pattern in homework 5, is first you're going to do just this point-to-point, so process to process communication, point-to-point. So you take this block in column j equals 0, send it to column j equals 1. And then this block j equals 0, j equals 2, j equals 0, j equals 3. Okay, so this is just a straight send, receive. So if you're this guy, you send, else if you're this guy, you receive. Okay, so just do that. It's going to be a bunch of send-receive pairs with if-else statements. Okay. Now next step, so this actually is quite fast because, for example, if you just look back, just sort of very high level, in the previous implementations, you know, for example, the first step is, each process had a piece of B, but then you wanted to do a collective communication so that all processes had the entire B. Okay, so that was actually quite expensive communication, whereas here, this is just sending this guy, so just a piece of B to another process. Okay, so the amount of data you have to send is much smaller, just a small chunk from one process to another process. So it's actually quite efficient. And after that, the second step is actually also quite efficient. So you want to essentially broadcast, okay? That is, you want to take the block you have in each column and broadcast it in the entire column. So for example, the block 1, broadcast the entire column. The block 2, broadcast in the entire column. Okay, broadcast and broadcast. Okay, so this is going to be a broadcast operation. So it's a collective operation, and use the bcast or broadcast function in MPI to do that. And again, this is going to be very efficient. First of all these broadcasts are sort of independent, so they can all happen very efficiently. And you're broadcasting only a small amount of data, because it's just a chunk of B, and you're broadcasting only to a small number of processes. Here, these groups of 4 processes. So again, this operation is actually going to be quite efficient and faster than the previous, for example, operations that we're doing, such as, again, remember that in the row partitioning, each process had a chunk of B, and then you had to do this gather so that all processes had the entire copy of B. So this is a much more expensive communication. So here, so far, the block decomposition is paying off. You're just sending much less data, and you're sending it to sort of fewer processes, only inside a column. This is enabled by this block partitioning. Okay, so essentially 3 steps.
I have a question.
Yeah.
Sorry, can we go back to the last? Yeah. Do each of these squares correspond to one processor or a thread, or like it's just the actual data?
Okay, so well, it's sort of a combination of everything you said. So essentially, it both represents the layout of the processes on a grid. Okay, so this is different processes. Okay, and so it's shown. So here, what I'm really showing is just the layout of the processes. In earlier slides, it was showing the matrix, how the matrix was mapped onto processes. But here, this is showing how the B data is moved about between processes. So for example, this is showing, a send receive from one process to another process. Okay, and then this is showing a broadcast, for example, one process here to all the process inside this call. Okay, so it's a broadcast in a set of 4 processes. Okay.
So processes means threads?
Well, it means no. So it's an MPI process. Okay, so it's not thread. So remember that in MPI, the way it works is essentially on each. So it can be done in different ways, but essentially you start independent processes or independent programs. Okay, so it's like, for example, if you have I don't know, if you have 4 computers. So you can do this in different ways, but let's say, for example, let's say you have 4 computer nodes, and they each have 2 threads, or let's say 2 cores rather, to be more correct. Okay, so 2 cores. So what you could do in the MPI, okay, is say, for example, MPI run -N8. Okay, and then you have your program here. Okay, -N8. So let's give it a name. Let's say the program is called just A. Okay. So what it's going to do is actually it's basically the same as logging onto these 4 nodes, and I don't know, from a terminal, running this program but twice. So it's actually starting the program twice. Okay, let's say from the terminal. Think of it in this way. So every time you launch an executable, say from the terminal or otherwise, it creates a process. Okay, so this is different from threads. Processes are much more sort of independent, and for example, a process cannot read and write the memory of another process, right? It's kind of protected. So they're sort of independent. So here, you're going to run these independent processes. If you do a top, then you will see, each process with a separate line. Whereas when you have a multi-threaded code, you would just run a single instance of the program, okay? And this program will have multiple threads, okay? And so, for example, if you do a top, you will see only one copy of this, only one of those. And also the threads, because they're threads in the same process, they have the ability to read and write memory between each other. Right? They can access the same memory. Basically, they can access any memory that's allocated for this process. Okay, so MPI is really looking at the level of running independent programs or independent processes, and therefore the data exchange has to happen through MPI. Okay, and so here, for example, each square, in this diagram, represent one of these programs or processes running on a node. So you can think of it as, for example, it could be a machine with 4 nodes, and maybe each node has 4 cores. Okay, so here you'd have 4 processes running, presumably each on one core, on a different core, but again, the operating system is doing that. And then here you'd have another node, and another node. Okay, and you have all these guys running. Okay, and you can exchange data. And so you can see that, for example, if 2 processes are on the same node, then the data exchange is sort of a shared memory data exchange. It's just a memory copy. If they are on different nodes, then it has to go through the network. It's much slower. So anyways, MPI sort of takes care of kind of optimizing the communication based on where things are. Okay, any other doubts? Okay, so in homework 5 you have a very similar sort of setup here. So just to summarize, so you first start with moving B from the first column to the other columns. So again, it's just real fractions of of chunks of B. Okay. Then you have a broadcast in each column. Okay. So this is the last step. So you do a broadcast. Once you have a broadcast, then you're good. Okay. Each process, okay, each one of those now has the block of B it needs, and it has the corresponding B. so you can just do the matrix vector product, with the data you have. So no more communication required. So this is what I called the local matrix vector product. Local meaning that there is no exchange of data or MPI calls, it's just a straight A times X, product. Now, when you're done with that product, then what happens is everybody has just a partial result for X, and you need to, there's a sum here. So again, this is going to be simply a reduction. But the reduction, again, is very efficient because you only do a reduction across the small piece of the vector, and the reduction happens across only 4 processes here instead of like everybody. Okay, so if you have 16 processes, sort of only 25% are involved in each reduction, so this can be done much more efficiently. Okay. So, so if you look at the algorithm, maybe you can feel that this is going to be more efficient. First of all, we have this 2D block partitioning. So, for example, here I could use 16 processes. If it was just doing row partitioning, it would be only 4 processes. So already I can use a lot more processes, okay? And I should expect, to go faster with the result. But then if you look at the pattern of communication, you'll see that, in fact, each process is even sending a lot less data around, okay? So you have this point-to-point initially, and then there is some broadcast, but it happens inside each column only, and there's some reduce happening in each row. But again, the reduce is basically just doing a reduction across a small chunk of data, okay? So it can be much more, can be relatively efficient. So we feel that this should go faster, but let's see how we can quantify this. Okay, so this is step 4, reduction across columns. Okay? So this is sort of a summary of what I said. So, we don't have any sort of communication that involves sort of all processes exchanging the entire vector B, for example. Only small chunks of B are being sent around, okay? And only subset of processes sort of need to communicate in this approach. So it should be more efficient, okay? And then, like I said, for example, if you have this partitioning into 16 blocks, 4 by 4, then in 2D block, you can use up to 16 processes, whereas in the row partitioning or column partitioning, it's only 4 processes. So it seems that we can use more processes in this 2D partitioning. So the question is, well, can we do the math and sort of demonstrate or quantify the improvement? And so when you do the math, there's one thing which is running a benchmark, which in some sense gives you the real running time. But running the benchmark is tricky because it depends on the specifics of the hardware. And if you run the same benchmark, you get different results and so on. And it doesn't give you a lot of insight really in these algorithms. So the better approach is actually to derive a theoretical model of the runtime. It's a simple model, but as long as there's enough in it to do the analysis, then this will work out. So we're going to come up with a model of the running time of each algorithm, and then based on this and this concept of isoefficiency, which you need to work on for homework 5, we're going to be able to compare these algorithms and determine which one is the most efficient. Okay, so this is a very important concept, though. If you write a paper on parallel computing, you definitely want to discuss your algorithm in these terms, and it's not always done. I mean, good papers, this is done, but not everybody does that. But these are extremely useful tools to kind of understand the efficiency and performance of algorithms. So there's a number of things that I'm going to have to kind of define to kind of understand, how to think about the efficiency or performance of an MPI code. So first on notation, so TP of n, the basic notation, this is a running time. P is the number of processes, and n is some size parameter. So here it's just going to be the matrix size, okay? So TP of n is the running time of my parallel code. So generally speaking, so if you want to analyze the running time of the code, in principle, there's going to be some time when the processors are doing computation. Okay, that's pretty obvious. There's some time dedicated to communication, and then sort of related to that, there is some idle time. Okay, when you're essentially maybe you have nothing to do. Okay, you're waiting for some data to arrive, but for example, the data is not ready, so it's not even being communicated. You're just waiting for the data to be computed somewhere. So there's some time that needs to go, where you're idle, and you're neither computing, you're not doing any communication. You're just, because of some dependency, you're just waiting for some other process to finish some computation so that some data that you need becomes available and hopefully can be sent to you across the network. Okay? So idle time is difficult to model. So here we're just going to focus on computation and communication, and we're just going to just have a very straightforward analysis where we're just going to look at how long it takes to do the computation, and then look at then the communication time, and just add those together. Okay, so generally speaking, there are various optimizations you can do to make it better, but here we're just going to take this simple kind of approach. So now, very important is the speed up, but even more important will be efficiency. Efficiency is actually the real concept we're after, and it's built on this concept of speed up. So speed up is a fairly obvious concept. It's simply the result of what's the running time in sequential divided by the running time in parallel. Okay, makes sense. So for example, maybe in sequential this is 1 second. In parallel, it's half a second. Okay, so it's 1 divided by 1/2. The speed up is 2 in this case. Okay, so it's the sequential runtime, that's a big number, divided by the parallel runtime, that's a small number. Okay, so the speed up is always a number greater than 1, and hopefully, and you want the speed up to be as large as possible. The speed up very, very large means that the parallel running time is very, very small. Okay, that's what you want. So you want a very large speed up. So fortunately, the math matches the English, meaning of the words. Right. So now, but moreover, you have this result. And so this is the key. So here, the idea is, okay, well, you're going to run your benchmarks. You're going to find some speed up. You vary P, you vary N, you get different speed ups. Now the question is, well, what is good and what is bad? Okay. So the idea is as follows. Let's say that this is 1 second. Let's say you assign 2 processes. Okay, ideally it's half a second. So the speed up is 2. Let's say you assign 4 processes. Okay, if you assign 4 processes, ideally this would be a quarter of a second. Okay, quarter of a second. So just so we don't get mixed up in the numbers here. Okay, so you have 4 processes. Okay, and the running time is a quarter. Okay, this is ideal. I'm running 4 times faster, so the speed up is 4. Okay, so you can convince yourself that essentially, in the ideal case, the speed up should just be linear or equal to the number of processes. So just linear with the number of processes. Okay? So this is ideal, meaning that when the number of processes is not too big, this is going to be roughly true. But as P increases, this becomes less so. At some point, S may just become constant. Okay, meaning that there is essentially no acceleration, although you keep adding more and more processes to your calculation. The running time is constant, so speed up is constant, and this is, of course, something to be avoided. Okay, so here I'm just going to go briefly over that. It's not super important, but it's just sort of a kind of a high-level thing to keep in mind. Actually, this is more sort of a practical lesson rather than mathematical equation. But there is a simple concept, and it's concept itself is kind of wrong, but it has some useful insight into it, which I want to get at. So in Hamdall's law, what you say is so again, you're looking at the speed up. Okay, you want the speed up to grow like p. Okay, and you write it as the sequential time, and then you divide by the parallel time. Okay, so how do you estimate the parallel running time? So in this simple formula, you're going to say, okay, there is a fraction f of the program that is serial. Okay, cannot be parallelized. Okay, so then the running time is just the sequential running time, so t1, but it's only fraction f. So now, 1 minus ft1, this is the remaining fraction, so the rest of the program. Here you assume it's perfectly parallelizable. Okay, so again, it's pretty simplified, but let's say that this is perfect. So the running time is divided by p. Okay, the fraction that's serial, fraction that is perfectly parallel. Okay, so running time is divided by p. Okay, so now you do some simple math. But I don't know, for some reason, computer science, even a simple math operation, a great deal of credit is given to it. So I'm going to divide by t1, and I get this equation. Right? And now you can ask yourself, well, if I increase p, what happens? Like I said, as you increase p, you want the speed up to behave like p, okay, to go linearly like p. So if f is very, very small, can be neglected, you see that indeed this is almost 1 over p, so the whole thing is very close to p. This is good. But as p increases, this eventually needs to go to 0, it becomes small, and it doesn't matter how small f is, ultimately f dominates. So here you can do a simple check. Well, basically this being positive quantity, then there's an upper bound 1 over f. So this is saying that the speed up, as you increase p, first is going to go up like p linearly, but then it's going to plateau at this constant. Okay, so you have that. So you have this curve here that kind of illustrates various types of speed up depending on the fraction of the code that's parallel. So here, very sequential code, more parallel. Here, this is a very parallel code. So initially, you have a very nice speed up, but then it sort of tapers off, towards the end. Okay. Increase number of processes. So here, okay. Well, so a couple of, let's discuss this result. First one is, actually this is kind of interesting because when I did my first internship 50 years ago, give or take a decade, the guy told me parallel computing is absurd because of Andal's law. Because you kind of feel that, actually on the face of it, this is really bad. Because, if I look at this law here, if I say, oh, if 1% of the code is serial, and 1% that's very small, then when p hits 100, that's not that large, then actually you're done. No more speed up. So the error in the reasoning, though, is that the fraction that is sequential typically goes down, or hopefully goes down, but in many cases it does go down with n. So it's not actually constant. Okay? As you work on larger and larger problems, this number here goes down, so that in fact you can see nice speed up even for a very large number of processes. Okay. But the more important take-home message, so this is the first bit, the more important take-home message is that, and that is definitely true, and this is something that we've actually seen already when doing CUDA programming, which is you're going to take your code, and there's this part of the code that takes a lot of time. So just to take a practical example of what some of my students in my group are doing, is you run a fast linear solver for x equal b, and you write the solver in parallel, because that's of course where the meat and the action is. But there is often a lot of stuff you need to do, like the pre-processing, which is basically reading in the matrix, kind of distributing the matrix to all the processes and so on, and doing various operations of this type, which in principle don't take too many flops, But the problem is if you want to scale to very large problems and really use a lot of processes, then this little bit of pre-processing you do at the beginning then becomes a bottleneck. Like typically you run out of memory, or you could even take a lot of processing time. Okay. So what's happening is, when you go and parallelize your code, first you look at the parts that take the most time, and then you parallelize these parts. But then those go very, very fast, and as speed increases, the time that these parts take can really go down massively. And then other parts of the code that seem to be, not very important, start to dominate the running time, and now you have to tackle those. And so what this is saying is, when P is not too big, then parallelizing your code is not too hard. You just go with these big routines and you parallelize them. But as you keep increasing P, it becomes harder and harder, because essentially more and more pieces of the code need to be parallelized until essentially every little piece of processing that's happening in your code is parallel. Okay, and then you can really scale to very large problems. And so the take-home message is, therefore, this is the CUDA optimization loop, is, profile your code, see what takes time, parallelize this, then increase P, but then you have to constantly rerun your profiler to figure what is the new bottleneck. Okay, and it's going to pop up from unexpected places. Now you parallelize that, it goes faster, and you just keep going like this. So this is very similar to what we had with CUDA. Okay, so let's go back to this analysis, and let's then apply to our matrix vector product. And in homework 5, you're going to apply this to the matrix product. So first of all, I hate speed up. Everybody talks about speed up. Well, I'll tell you why everybody talks about speed up. Because speed up goes up. So, it's good. Even if it goes up slowly, you can say, see, it's going up. But the real thing is, what you're really after is, ideally, the speed up goes up like P. So what you really want to know is it going up like P or slower than P? Okay, that is the real question you're after. For example, if it goes up like square root of P, that's no good. Or log P, that will be terrible. Okay? So hence, the better thing to look at is the speed up divided by P. Because now that's just a fixed number. Okay? It could actually, you can think of it as 1 being the best, but in practice, you just want it to be constant. Okay? And so it's T1, serial running time divided by P times parallel running time. Actually, this number is very seldom published, mostly because it doesn't look as good as S, right? Because the speed up always go up, whereas if you divide by P, now it will definitely go down, okay? And the best you can do is just making it constant, okay? But this is a real quantity to look at. And so, for example, you can see that if the speed up is constant, so basically you're adding more processes, but the running time stays the same, actually that guy will go down. And that's correct, because it's telling you that there is a problem. That actually, your code is not really scaling, you're adding more processes, and it's not going any faster, because there's definitely a problem. So the efficiency will go down, and in fact, this is what you want to see. Okay, so ideally, the efficiency remains constant as P increases. So now, what is sort of the mental picture you should have about the efficiency? Okay, so there's basically two just very generic concepts or things to have in mind, which is that as you increase the number of processes, pretty much the efficiency can only go down. Okay, at best it's flat, but it's going to go down. And essentially, what you want to know is, let's say you want your efficiency to be above 0.4, 0.2, then you want to know, well, how many processes can I assign to my calculation before it reaches that efficiency? Okay. So it has to go down, and hopefully it goes down slowly, but that's the first mental picture. Second mental picture is that if you solve a larger problem, of course it's not always true, but in most algorithms, if you have more work to do, the efficiency will go up. Okay, we've seen this in CUDA and so on. So if you're processing a larger matrix, then typically the efficiency will go up as you increase the size of the matrix or the amount of work that needs to be done. Okay, so typically, as you increase the amount of work, then each process has a lot more work to do, and if your algorithm again is written correctly, you have, relatively speaking, less communication relative to the computation, and so the efficiency tends to go up. So these are two mental pictures you want to have. Okay, so let's apply this to matrix vector multiplication. So there's a little tidbit about modeling collective communication, but this I'm going to skip because it has to do with hypercube networks and the topology of the network and so on, and it's not super relevant for us anyways. So what I'm going to just show you is give you a table that you can simply refer to that gives you the running time. Actually, in the homework, we're giving you the formula to use, but just as sort of a reference, here's the table. It's essentially telling you for all the collective communication, the time it takes to perform the communication. So actually, let's look at the bottom one, which is circular shift means essentially you're sending a piece of data, let's say to your right, and receiving a piece of data from the left. Okay, so it's basically just a point-to-point, actually. And it's written in this fashion, okay? And this is how you model communication. So there's a time for latency and a time for bandwidth. So the time for latency, this goes back to this idea of pipeline, that if you send just one byte of data, it's going to take a certain amount of time to send it across the network no matter what, right? So this is the latency, okay? But now if you send a lot of data, if you send a gigabyte, then this latency becomes negligible, and now the running time simply becomes linear in the amount of data you're sending. That can make sense. Okay. And so now it goes linearly with the amount of data you're sending, so M is the amount of bytes you're sending, and TW is the inverse of the bandwidth, okay, or it's the number of second per, let's say, byte that the bandwidth gives you in your network. How many seconds it takes to send one byte, but assuming you're sending a lot of them, you're sending like a gigabyte worth of data, so it's the bandwidth. So TW is the inverse of the bandwidth. And then you can look, so I'm not going to go through the entire table, but for example, the broadcast, which is one to all, so you have different implementations of the broadcast, but roughly speaking, you can recognize that you're using a tree structure, okay? And so you're going to have log p passes that need to sort of happen one after the other. So you have log p passes times the time to send a piece of data. So it goes like this. Similarly, you have, so for example, scatter is very similar, so you can recognize tree structure with the latency. But here, because it's a scatter gather, it's the amount of data times the number of processes is what you have in front of the bandwidth. So anyway, you have this table that you can use to evaluate running times. So whenever you have log p term, it actually means that you have a very fast algorithm to, based on the tree structure, to do your communication. Now this assumes the hypercube. Hypercube has to do with the topology of the network. As it tells you essentially something about how long it takes to exchange data between any two nodes of your network, and so you want to of course use the fast wires instead of communicating between nodes that are very far in the network. You want to communicate between nodes that are very close and are directly connected by a wire. And so these algorithms make use of this hypercube structure when scheduling their data exchange. So anyway, for us, these are maybe technical details. We just want to use the formula. So in the homework, it's given to you. So these are the notations in table. M is size of the message in bytes. P is number of processes. T is the latency. So the time it takes to send just a tiny piece of data. And TW, basically, this is the time it takes if you send a large amount of data to the reciprocal of the bandwidth. So let's apply to matrix vector product. Okay, and you have to do something very similar in homework 5. So here I'm just going to give you a bunch of formulas. I mean, the details don't really matter, but try to get the high-level ideas. So hopefully you can apply the same ideas in homework 5. So first you start with the serial time. Okay, so when you do matrix for homework 5, it's n cubed. For matrix vector, it's n squared. Okay, so this is a reference serial running time. Okay, and then you have to estimate the time it takes to do the computation and the communication. Okay, so here's row partitioning. So this is the time for computation. So you have, it was partitioned across rows. So it's basically the total number of flops divided by p. So alpha n squared divided by p. And here you recognize, for example, we had the scatter or maybe the reduction. So depending on, so the row partitioning was actually a scatter. So with the tree and so on, so there's a log p term. So now let's just plug in this formula and let's see, well, what do we get with for the efficiency? So efficiency is T1 divided by P parallel running time. So this is the parallel running time, so just the previous formula multiplied by P. Okay, you get T1, so you get this ugly looking formula. So when you look at this, the main question we're going to be after is the concept of isoefficiency. Okay, so what isoefficiency means is that, again, if you look at this formula, and for example, you increase P, you see that the efficiency goes to 0. Okay, so this is what we said. If you assign more processes to your calculation, the efficiency has to go to 0. So this is what we see here. You increase P, the whole thing just goes to 0. And vice versa. If you increase n, the matrix size, okay, if you increase n, then this is the opposite. The efficiency goes up. Okay, asymptotically, the efficiency goes to 1. If you increase n, this goes to 0, goes to 0, goes to 1, so the whole thing goes to 1. Yeah.
Sorry, I might have missed this, but how did we come up with the expression for G sub B?
So this guy here?
Yeah, well, the line above it.
Oh, so this is just this was just the previous slide, right? So just P times TP. So where we estimated the running time for the computation and the running time from the communication based on this table that I gave you. Right, and that was
the second two terms are from the table.
Right, yeah. So this term is basically, so you have to look at exactly which one it was. But I think it was probably a scatter, if I'm not mistaken. So it should be log P plus MP. So let's see if this works out. So we definitely have log P. And then second term is MP. So that should work out because, everybody has basically N over P times P. Okay, so basically this was just reading from the table and applying, the result from the table, and then this is just a computation. So this is homework 5, we're giving you this formula, so no worries there. Okay, so coming back to that, again, as you increase the number of processes, the efficiency goes to 0. If you increase the problem size, n, then the efficiency goes to 1. Okay, so fine, this is the usual trend in these algorithms. It kind of makes sense. So what do we do with that? Okay, so hence enters the idea of isoefficiency. So isoefficiency means, let's say the efficiency is 1/2. Okay, I want the efficiency to be 1/2. Then again, if you increase, let's say the efficiency, you can think of it this way. Okay, this is the target efficiency 1/2. Okay, if I increase P, okay, then the efficiency will go down. At some point, initially it will be larger than 1/2, after it will be below 1/2. Okay? And then vice versa. If you increase n, then the efficiency goes up. So maybe you start with a very low efficiency, increase n, okay, you get above 1/2. Okay? And so this point here is special, okay? The efficiency is exactly at 1/2. And so the question is that there is a function, right, such that if P is equal to f of n, so the function is going to be something I need to figure out, but there's a relation between P and n such that the efficiency stays exactly at 1/2, or generally speaking, just a constant. Okay, actually, the exact constant doesn't matter. What we're after is what is this relation between P and N such that the efficiency is constant. Okay? And basically what this tells you is as you increase the size of the problem, how should you increase the number of processes such that the efficiency is constant? So if you increase P faster, the efficiency will go down. If you increase P slower, the efficiency will go up. And if you increase P exactly with this relation, then the efficiency will be exactly constant. Okay? So mathematically, of course, this is sort of a mathematically a trivial result. You just say this function equals constant, and then implicitly, this gives you P as a function of n. Okay? So it gives you, actually gives you a curve. Another way to interpret this is if you look at this in the Pn plane. Okay, so maybe so maybe this is n, and this is P. So if you're along this curve, then the efficiency may be, say, 1/2. Okay. If you're above, then the efficiency will be below 1/2. And if you're below, then the efficiency will be greater than 1/2. Okay, if you're on the curve, efficiency is exactly 1/2. And in fact, you want P to be a good program will allow you to take P very, very large, assign a lot of processes to your calculation while being very efficient. Okay, a bad program, well, to be efficient, you can only assign very, very few processes. Okay, so you'll be below. So it's kind of, it takes some time to wrap your head around this, but it's actually a very, very powerful concept. So the question is, as efficiency, how quickly can we increase P such that the efficiency is constant? Okay, and I want to go over a couple of calculations. So I'll give you an exercise at the end because I want you to do it on one exercise, so you can do the same thing for homework 5. It's actually a very simple process, but the first time you do it, it's very counterintuitive. But once you get the hang of it, it starts to make more sense. So, so here is the efficiency we have for the row partitioning. And when I say I want to be isoefficient, I want E to be constant. So what does it mean? Well, for E to be constant, you want this expression here to be constant. Okay. So if P, let's say P is proportional to N, let's say that P is proportional to N. That's the answer. If P is proportional to N, then definitely this term is constant. It's not going to 0 and it's not going to infinity. And now this one is N log N divided by N squared. So basically it's log N divided by N. So actually this term goes to 0. But that's fine. So it's 1 plus 0 plus constant. Okay, the whole thing is constant. So if P is proportional to N, the efficiency is constant. So that is a rule. You cannot increase P faster than N in that scheme. So if you increase P faster, the efficiency goes down. If you increase P slower, the efficiency goes up. This tells you how quickly you can increase P. Okay? Everybody follows that? So we're going to do the same thing for the 2D block scheme, but I'm going to ask you to give you a couple of minutes to kind of do that. So there's more slides, but the second part is, I'll do that on Friday. Basically, I will just start discussing communicators and groups for homework 5. Okay, so let's look at 2D block scheme. So here again, I'm going to skip the sort of theoretical analysis because that result is given for you in homework 5. So I'm just going to go very briefly. So this is the amount of computation. Well, it's always n squared divided by p. That's just that's always the same formula. Then sending b to the diagonal. Okay, it's almost the same as before, but now you have square root of p because it's a 2D block structure. Okay, and this is the piece of b that you have. This is just a point-to-point communication. Then there's a broadcast. Well, it's the same thing. So now there's a log. You're going to do a tree, but this is a broadcast in the column. So this is log against square root of p. And the amount of data you're sending is square root of p, because this is just one column. And then the reduction inside one row or across columns. So actually, this is just the same expression. So the log is because of quality communication, and the square root of p is because of the 2D blocking. So you're winning because of essentially this square root of p that you have in this 2D algorithm. Okay. So first I'm going to give you the result, then a little bit of interpretation, but then I'll come back to this result because this is the bit in homework 5 that's a little bit more difficult to figure out. And I want to go through derivation, or I'll let you work a little bit through that so you understand the process. So here is the efficiency. So again, this is T1 divided by PTP. So if you go back, so here I'm skipping it, but essentially you add all these terms. Okay, this gives you TP, and then PTP divided by T1 is just this crazy formula. Okay, and then we're going to come back to that later on, but just to sort of continue this discussion, what you find is that if P is equal to n squared log square n, then you have isoefficiency. So if P satisfies this rule, then you can check that this term here is constant, and this term here goes to 0. Okay, so you can see a little bit why this is the case. N squared simplifies. Okay, you divide by log n, everything square. This is basically log n, so you get 1 over log n goes to 0. So this whole thing goes to 0. And now you can also evaluate this one. It's constant, 0, 1, efficiency is constant. So now the question is, okay, if you compare the row partitioning, P increased like n, and here P increased like n squared divided by log squared. So basically, in the second case, this is the plot. In the second case, the 2D blocking is at a much higher isoefficiency curve. Like the P is higher. Okay? So here, for example, this is, this is basically n, or the work size. Okay? And then this is the isoefficiency. So this is P. This is P as a function of n, or the isoefficiency plot or curve versus the work size. And so for row partitioning, it's n, this guy. For 2D blocking, it's n squared divided by log n squared, and the green is just n squared. Okay, so 2D partitioning is higher than row partitioning. This means that you can assign a lot more processes for the 2D partitioning while maintaining efficiency, which translates into simply the code runs faster. Because you have a high efficiency, but you have more processes, that means the code strictly runs faster. Okay, so the higher the isoefficiency curve, the faster your algorithm is going. And so you can see how now we start with all these complicated formulas, but just simply by doing these plots, then we can figure out, well, which algorithm has the highest curve is on top, and that is the winning algorithm. Okay, so the higher isoefficiency you can have, the better the algorithm will be. So here, we're winning with the orange method, the 2D blocking. Okay, so higher efficiency plot is better, so you can maintain the same efficiency, but with a larger number of processors, means the running time is just strictly lower. Okay, but this is a nice way to visualize this. So let's. So here I'm going to let you sort of work on this now as a little exercise. So if you can take out some pencil and paper, I want you to start from this formula, and then try to figure out the isoefficiency relation that I gave you, sort of re-derive that. Okay? So hopefully in this day and age, you still have paper. If not, you can elbow your neighbor and grab a sheet. What's that? Oh, yeah. So if you have a stash, you can pass it around. I need a pen. Okay. Actually, I need throw some pens. Maybe I should give this. I got one. Okay, so all right, so everybody gets a pen and a paper. Okay, and you want E to be constant, so this is the same as this being constant. So now the question is, well, we know, I told you that once you're at isoefficiency, this term is constant, and this term goes to 0. But how do you know that? Okay, so the way to go about this is to basically, essentially, when you do isoefficiency, you're going to have the sum of a bunch of terms. One of them essentially is going to be constant. the other ones are going to go to 0. If you pick the wrong one, okay, then the one you pick will be constant, but the others will go to infinity, okay, meaning the efficiency goes to 0. So that doesn't work. So the way to make it work is you're going to say, assume this is a constant term. So you make this equal constant. So basically, P is n squared divided by log n. Now, assuming this relation, you plug in here, and you will see that this goes to infinity. Wrong. Okay, second assumption, take this, set it to constant. So now P is going to be n squared divided by log n squared. Plug in here. Oh, now this goes to 0. Correct. Okay, so that's how you do it. Take each term, assume it's constant, check the other one. If the other one goes to infinity, wrong. If the other one goes to 0, correct. And you could, you know, if you had like 5 terms, you could just do the same thing 5 times. So I'll let you work on this, and yeah, and then maybe I'll give you a solution. So actually, I'm going to start writing up some stuff here on the board. You can help you along. But I want you to do it, not look at the board. Because there's just a little piece of thing I want to talk about. Okay, so I'll give you a couple of minutes to work through that. And then I'll give you a solution. And then we'll just wrap up the class. So you should be able to work out at least the first term. Okay, so we're almost at 50, so I want to kind of wrap this up. So, you probably got this expression. This corresponds to taking this term here and saying it's constant. Now the thing is, you want p as a function of n, and here you have log p. So you may wonder, I'm stuck. How can I solve this? Okay, well the idea is you really just want something of this form, a big theta or essentially a big O. So the constants don't really matter, right? You want just the leading terms, okay? And it turns out that in all these relations, you can prove it, but log p simply behaves like log n. So the simplification is therefore trivial. You can just write log n. So essentially, the next term is something like log n, but that's negligible compared to log n, so you can just ignore it. Okay, so to first order, log p can be written as log n. Okay, so this is one little bit here that's kind of important to get something that only has n in it, and you don't have to solve, p log p equal n, which is not very easy.
I tried.
Well, I mean, of course, there is a solution, and it could be computed, but because you only want the analytical expression, so here there's some extra. Actually, if you do an expansion, you get log p and additional terms. But the first order, this is just log n. Okay, so I'll just wrap it up here.
Can we get a log squared p, or are we ignoring that?
Well, in principle, yeah, it's log. Technically, you could write it as log n squared, but then the 2 goes out. It's 2 log n. So in terms of the constants, you just say log n.
But I think p should equal c times n squared divided by log squared p, not log.
Well, that's no. So the log p squared, this is what you get in the second term, actually.
Right.
Right. So if you assume that this one is constant, okay, then you get n squared divided by log n. And then you can see that the second term, so here I'll skip, but the second term you can check goes to infinity. Okay? If you make this assumption, then you get log n
okay.
squared.
I was skipping this stuff.
Right. So, okay, now you get the square. Okay, so the second is constant, and now first one goes to 0. Okay, so that is the correct one. So hence the correct answer is the second line here. Okay, this is the one that makes sure that this term is constant, this one goes to 0. If you try the first option, this one is constant, this one goes to infinity, so efficiency goes to 0, so clearly that doesn't work out. Okay, so all right. Okay, another way. So sorry, just another thing. So no, this is another interpretation I had in the slides, which is once you get these two relations, you can also check which one is the lowest one, like the most restrictive, and that is the correct one. This is another interpretation by looking at the most restrictive answer, so which is dividing by log square n is the most restrictive, and so this is the correct answer. Okay, so I think this is it. Okay, so all right, so end of the class. So you can, if you want to stick around, or I can answer further questions about this analysis. But that was all for today's lecture.